Hello and welcome to Carlem Cymru e-sgol sessions. My name is Mr. Rid, and as soon as I get past this little technical difficulty, which I seem to be having right now, we'll make a start on AS Unit 3, no, Unit 2, sorry. AS Unit 2 past paper practice. Now, we're going to be looking at, if I can find the cover sheet, yes, it's over here for some reason, 2018 Unit 2 Electricity and Light. So if you want to check in on the mark scheme, you know where to look for it, okay? Straight in then. Question number 1. Two 3.3 ohm resistors are connected in series across a battery of EMF 4.8 volts as shown. The voltmeter reads 4.33 volts. State, in terms of work or energy, what is meant by EMF. So, what is meant by EMF? That is that right. So let's get cracking. It's the energy / work done, okay, per coulomb of charge. This bit's really important. It's often missed off. All right, the per coulomb bit really is essential here. It's not just the energy; it's the energy per coulomb of charge. All right. Transferred. Sometimes it's put down from chemical to electrical energy by a power supply or cell, battery at a push. Show that the internal resistance R of the battery is approximately 0.7 ohms. Now, as you'll have learned, when we have a cell or battery in this case, they will within themselves have an inherent internal resistance, such that when a current is flowing, some small proportion of the voltage will be dropped across that internal resistance. Now, we have to show here that it's approximately 0.7 ohms. To do that, we are going to sort of think about what the really total resistance is, right? And we've got these numbers up here we can use. We know that we've got a voltmeter that reads 4.33 volts dropped across those two resistors. So if we then use I is equal to V over R, we think about those two external resistors having a combined resistance of 6.6, and we know we've got 4.33 dropped across them. We've got 4.33 divided by 6.6, and that's going to give us let me get this right, 0.656 amps. All right. Now, it's 3 sig figs because if you actually look at the workings out, we've actually got 3 sig figs for the voltage and the resistance. So now that we know the current, importantly, we don't just know the current here. Oh, sorry, here. We know the current here. We know the current here. We also know now the current through this little internal resistance. And we're nearly there now. We nearly solved the problem. If we know that we've got this much voltage, right? So this much current, sorry, in the circuit. And if we also know the voltage dropped across the internal resistance, then we can solve the problem. How are we going to work out the voltage dropped across the internal resistance? Well, we know that the EMF, we're told in the question, is 4.8, and we know that the voltmeter reads 4.33. So we can actually determine then that the internal resistance, or if you like, the voltage dropped across the internal resistance, I should say. All right. So if you like, we call this V subscript R is going to be 4.8 minus 4.33. And that comes to, oh, let's see. Oh, that's how we'll work it out now. We'll say that, yeah, well, we'll work that out. So that is 0.47. That's the voltage dropped across the internal resistance. And then finally, little r then, again, just using Ohm's law, is equal to V over I. The voltage, 0.47 over I, which is 0.656, gives us an internal resistance of approximately 0.72 ohms. Okay, moving on. What's it doing this? Gremlins tonight. When the resistors are connected in parallel, as shown below, the voltmeter reads 3.35. Okay. So, without further calculation, explain why you would expect the reading to be lower now that there is a low resistance across the terminals. A couple of options here, a couple of different ways to answer it. First of all, you could say, or maybe this is a fine one to use, less resistance. Because remember, when we arrange resistors in parallel, the resistance goes down. Less resistance means greater current flows. Right. We've got a greater current, then from Ohm's law, okay, because V little r, the voltage dropped across the internal resistance, is equal to I times R. The voltage drop across internal resistance increases. Now, as a consequence of that, then, the voltage supplied to the circuit and those two external resistors goes down. Therefore, voltage to circuit goes down. Excellent. Right. Calculate the number of electrons entering either of the resistors shown in diagram 2 per minute. Okay. So to know the number of electrons, it'd be really handy to know what the charge is. All right. Because if we knew the charge passing through those resistors in a minute, and then knowing the fundamental charge of an electron, we could work that out. Fortunately, both of these resistors are the same value. So because of the same value, they will have the same amount of current flowing through either. Now, the amount of current flowing through one of these, we can use Ohm's law again. I is going to be V over R. We were told just previously that the current, or the voltage, sorry, goes down to 3.35. So that'll be 3.35 for both. So then we'll have 3.35 divided by 3.30. Which is 1.02. Then let's think about what an amp is. Well, 1 amp is equal to 1 coulomb of charge per second. And if we want to know then how many electrons in a minute, then the next thing we can do is say that, well, charge is equal to the current times the time. It's equal to 1.02 times 60 seconds. for that minute that we just mentioned. That comes to, let's see, 61 coulombs. Let me just double check that. Let's see, 1.02 times 60. Yeah, 6.61. I'll do coulombs. 61 coulombs of charge is a lot of charge compared to the fundamental charge of an electron. So the number of electrons is going to be 61 divided by the charge of a single electron, which is 1.6 times 10 to the minus 19, which is equal to, let's see, 61 divided by 1.6 e minus 19. Jane?
3.8 times 10 to the 20 coulombs.
Thank you. Thank you. It's very efficient. To the 20. Thank you very much. Okay. So that's just electrons then. Heating element, coil of wire in electric heater, dissipates energy at a rate of 1 kilowatt when connected across the 230 volt main supply. Calculate the resistance of the coil. Now, you have got three formulas when it comes to power and how it relates to, sorry, that's not really working. We've got P is equal to I times V. You should really know these. P is equal to I squared R, and P is equal to V squared over R. Think about what the question's given you here. We've got voltage and we've got power. And it's asking us to calculate resistance. So we're going to go with the last formula here. So then we've got R is equal to V squared. Now V squared is 230 over the power, which we were told was 1 kilowatt. Now be careful here. It's 1.00, so they're giving you actually three sig figs here, which is important to remember. This is 1 times 10 to the 3, and 1.00 times 10 to the 3. I should have written down really. Wow.
That comes out as 53. In case you.
Thank you. For some reason it keeps jumping around a lot, and it is really starting to annoy me. Yes, sorry, that number again, Jane?
53 ohms.
53 ohms, thank you very much. Right, next then, the heating element, coil of wire in electric heater, dissipated energy rate. Oh, we just did that one, it's all jumped around now, fantastic. The energy dissipated per hour, giving you an answer in megajoules. Right, so we just had the power, which is in kilowatts. And now the energy dissipated then over that time of an hour is just going to be simply power times time, right? So if you think about 1 kilowatt is 1,000 joules per second, okay? So that's 1,000 joules per second. That 1,000 joules per second times time, which is going to be 60 times 60 for our hour, comes out as equal to 36 megajoules. Okay. Oh no, sorry, 3.6 megajoules, I should say. 3.6 megajoules. Right, further down now. Right, for each megajoule of heat from an electric heater, approximately 0.08 meters cubed of gas would have to be burned in a gas-fired electricity power station. For each megajoule of heat from a domestic gas fire or boiler, approximately 0.03 meters cubed of gas is burned. Discuss whether the use of electric heaters in houses should be discouraged. Calculations are not required. Right, so essentially what this is saying is that if you were to use an electric heater in your house, more energy or more gas is being produced. That gas obviously would be CO2, and therefore we're producing 0.08 every megajoule if we're using an electric heater, and we're producing 0.03 if we're just heating our house by burning the gas directly in our homes. In other words, which is better? It says calculations are not required. So you just need to think about those two things. It is far less or far more efficient to use your boiler in your house to heat rather than electric fire. Less carbon emissions. Less carbon emissions is going to mean, of course, a lower impact on global warming and climate change. All right. Number 2, the resistance then of a thermistor varies with temperature as shown in the graph. We've got this little sort of potential divider circuit here. Determine the temperature of the thermistor when the voltmeter reads 1.2 volts. So let's have a look. If you've got 1.2 volts, I'll mark that onto our diagram here. And we've got 1 kilo ohm there. We've got a graph of the resistance there. So essentially what we got, nope, that's not right. Excuse me just a second. You rub that off. So when the voltmeter is 1.2, we've got to think about how this potential is divided between the two. Now, if I have got 6 volts here, it's going to be shared equally between those two components, or shared between those two components, I should say. So if I got 1.2 here, then that must mean I've got 4.8 volts dropped across the thermistor. All right. Now, 4.8 volts are dropped across the thermistor. I can now figure out what the resistance of that thermistor must be. And we can do it by way of ratio would be one way of looking at it. Oh my word. Nothing's working this evening. Oh my word, I can't even scroll down. What is going on? Excuse me. Big technical difficulties, right? So, wow. Right, determine the temperature of the resistor when the voltmeter reads 1.2 volts. So this must mean, if you look at the total resistance, okay, because the ratio of the voltages, because we've got 4.8 volts across the thermistor and 1.2 volts across the 1000 ohm resistor, I can say that there is 4 times the voltage dropped across the thermistor, which means that we must have 4 times greater resistance. So if you think about it in those terms, in terms of a ratio, I must have 4 times larger resistance. Therefore, we must have a resistance of 4. Sorry, I've lost my page here.
That's right, 4 kilo ohms.
5, yeah. The total resistance then is, if you like, RT is 5 kilo ohms, and then the R thermistor is 4 kilo ohms. Moving on. The setup can be used as a thermistor, with the thermistor used as a temperature probe. David suggests that there must be a simple rule of the type: an increase of 0.1 volt in the voltmeter reading corresponds to a temperature increase of n degrees Celsius, in which n is a constant. Without further calculation, discuss whether he's right. Well, in this particular situation, he isn't right. And the reason why he's not right is that the resistance isn't linear. So every change in temperature on here, or if you like, the gradient of the graph is constantly changing. And because the gradient of the graph is constantly changing, we haven't got a linear relationship. So I'm going to jump straight through that one and not write it out just in the interest of time. But that's the answer to that one. It isn't a linear relationship, and therefore we can't say that V is proportional to R. Explain why the current through the thermistor must be very low in order for it to work properly as a probe to measure the temperature of its surroundings. The temperature must be very low because, as you know, with components and resistance, when there's a flow of charge and when electrons are making collisions with ions in that material, then they will transfer energy. When they transfer that energy, it can cause atoms to vibrate and the material gets hotter. So if we use a high current, the thermistor itself will get hot. If the thermistor gets hot, then it's going to if you like, interfere with the temperature of the surroundings, and it won't be measuring the temperature of the surroundings. Moreover, it will be sort of measuring the temperature of itself. So something along the lines of it'll interfere with the temperature of its surroundings will be fine. You don't want to watch me write that down. I've explained it. You can do that if you download the paper and try it yourself. Okay, so question number 3. We've got a simplified energy level diagram for a 3-level laser system. And here we've got level P, U, and L. Calculate the wavelength of light emitted by stimulated emission. Now, first of all, we have to think about where the stimulated emission is going to come from. All right. And to do that,
20 minutes.
Sorry?
That's
20
minutes,
okay.
that, yeah. But we've got
Okay.
time.
Okay, I'll just I'll rattle through this bit as quick as I can. Okay, thank you, Jane. So to do that, we've got to think about where we'd have our population inversion, and we'd have our population inversion in level U on a 3-level system. All right. Now those electrons would be going from level U down to the ground state, and we want to work out wavelength. We have to do away with this electron volt business. We need everything in joules to be able to use E equals HF. Let's do that quickly now. So we'd have to first of all convert. So we'd have 1.79 times 1.6 times 10 to the minus 19, which is, don't forget, the conversion between electron volts and joules. All right. And that is equal to 2.86 times 10 to the minus 19 joules. All right. Now, next, we have to think about what that would be in terms of a maybe a frequency, or we can use this. Now, we've got E is equal to HF, but we've also got E is equal to HC over lambda. And then, really, if we arrange for lambda, lambda is going to be equal to energy, which we calculated just there, 2.86 times 10 to the minus 19, times C, which is 3 times 10 to the 8, speed of light.
Yeah, put the energy underneath.
Oh, sorry, yeah, sorry, my bad. So the energy should be underneath, my apologies. Thank you, Jane. So that's 2.86 times 10 to the minus 19. And then on top, then we've got Planck's constant, which is 6.63 times 10 to the minus 34. Okay, bit messy, I do apologize. And we end up then with a wavelength of 6.9 times 10 to the minus 7. And maybe why do we need population inversion? I'll finish this page and then we'll call it a day. Why do we need population inversion for light amplification to take place? Quite simply put, we need more electrons in level U to cause stimulated emission. We've got to have more up here than down here, because if we've got more in level U, the probability that we'll get an electron stimulated to jump down from U to L is going to be greater than an electron absorbing a photon to jump up, and therefore we'll get light amplification as a consequence. All right, I think there I'll leave that.
So Jane Owen from Penglis School joining James from Bridgend, and let's go through to 6, 7, and 8. And the reason why I've chosen these, because this has got kind of like some skills attached to it that you'd think, hey, that's not fair. We're not doing a practical paper or anything like that. We've done lots of practical, kind of experiments, but they are putting quite a bit of practical work within the actual papers themselves. So be prepared for this. So make sure that you've done all of the practicals, because you will be asked questions on them. So this one's all about standing waves, looking at stationary waves and using a tuning fork. And this person has got a series of values, repeated readings of X, and he has to, it explains how he gets those. and hopefully that you've done the same in the lab situation. And he's got a range of results for X. Now, let's just go on. Calculate the mean value of X along with its percentage uncertainty. So getting the mean is quite straightforward because we get all of those together. We can't see any anomalies there, so we literally add them all up, press equals, and then divide by the number that we've got, 1, 2, 3, 4, 5, 6, to get the actual mean value. All right, and put all of that working into the answer here. Don't just do what I've been doing. This is jumping around, but we will bear with it. And the answer there is 0.327 to get the value of the mean, X mean. Now we need to find the percentage uncertainty. And this is, expected for you to know how to get these percentage and absolute uncertainties. Now, to get the, we have to get the absolute first before we can get the percentage. So what we've got to do is we've got to find the minimum value, and we find the maximum value, and we get those two, 0.332, and take away 0.322, the minimum, and divide it by 2, because what you want with the absolute uncertainty in X is you want a plus minus. Okay, and so from whatever is in the middle, you have to go up or minus to get the minimum and to get the maximum. So that comes out, once you've done that, as to be plus or minus 0.005. Notice I'm only giving it to one significant figure. That's all you need to do, unless it starts with 1, and then you would have to add another significant figure to it. All right, and then to get, so that's the absolute uncertainty in X, and to get the percentage uncertainty in X, that will be the absolute divided by 0.327 times by 100%, and we've got 1.5%. Now, you're going to say, oh, okay, well, that's two significant figures now because the first number is a 1, okay? So we can leave it as 1.5%. So now we can use that equation above in part 2 to find the value of BS along with the absolute uncertainty. To find, you just slot it in. We've got the frequency. We've been given that, 256. So VS equals 4 times F times X. That's fairly straightforward. So 4 times 256.0 times by 0.327. Now, I would probably, so the answer there would be 335, and I would put that in as 3 significant figures, because the least number of significant figures here is the 3 significant figures here, okay, of our mean, coming from our X values. And that's okay. I mean, you are allowed one more significant figure, but as I would stick with 3 significant figures. Now we've got to look at the absolute uncertainty. Well, we've got VS equals 4FX as the equation. So the absolute uncertainty in VS is equal to the percentage uncertainty in F plus the percentage uncertainty in X, because we're using each of those values once and once only in the equation. The 4 doesn't have a percentage uncertainty because it's a constant. And we've been told on the previous page that the percentage uncertainty in F is 1%. The percentage uncertainty in X is 1.5%. So add the 2 up and you get a percentage uncertainty of 2.5%. Now, don't round it there because we haven't finished calculating. So now what you've got to do to get the absolute uncertainty is actually find what 2.5% is of the 335. And if we do that very quickly, 2.5 over 335 times by 2.5 over 100 times by 335 to get the 2.5%, and that's plus or minus 8. So therefore, the final answer you will show as 335 plus or minus, oh, let's put the units in first on that answer. Sorry, not to be moving along swiftly. You need meters per second. Plus or minus 8 meters per second. That ties in with the significant figure, the last significant figure that I decided to express the speed with. And that is consistent, okay? So there's a lot to do for your 2 marks. Now, derive the equation here, Vs equals 4Fx. Of course, you can stop the recording and you can read it properly, all right? Then is basically you've got your tuning fork here, you've got the end and the water, and there'll be a nodal point where the water is and an antinode where the ends is, where the tuning fork is. And that represents 1/4 of a wavelength, and that is the value of x. Okay, so if you've got your equation V equals F lambda, where lambda is equal to 4x, okay, 4 times by x, would have to times that x by 4 to get the wavelength, then you can substitute then in for the standing wave, f times by 4x, so you get 4fx. So a little diagram like that will suffice, okay? And then if you carry on, the next resonant wavelength at which resonance takes place will be the same, that you'll have a nodal point at the end here, and you'll have an antinode at this point here, and then you literally have to kind of like judge it to get an antinode, and then like that. It's quite tricky. So that would represent there, that value of x there would represent 3/4 of a wavelength. All right, and then so on. You don't have to restrict yourself to that first like harmonic of what you had before. You could go to the second harmonic and so on. So you could have a node, antinode, node, antinode. You know, you can have more. As long as you finish up here with an antinode and you finish here with a node, you can have any number in between. Okay, moving on. Question 7, refraction. So this is one of the revision topics that I did with you, recordings, using Snell's law. Okay, so Snell's law, N1, refractive index in medium 1, sine theta 1, equals N2 sine theta 2. Okay, now we use degrees here, and so the refractive index in glass is times by the sine of the angle in the glass is equal to the refractive index in air times by the angle, sine of the angle in air. So we've got all of that information. You've got 1.6 times by sine, and this is the, now if we've got our normal here, then we don't have to draw this to scale. And we know when the light is going from glass into air, is going to speed up, going into the less dense air. So it's going to bend away from the normal. So this is the angle of incidence with the normal from the incident ray going in. And then this one is the refracted angle coming out of the glass block with the normal. So we'd always take the angles to the normal for this. So 1.6 times sine 30 is equal to 1 times sine theta in air. So if we then, because we want to find the theta, the angle in air, i.e. the refracted angle, then it's just literally sine to the -1 of 1.6 times sine 30, and that gives us 53 degrees in air. Okay, and that is equal to the refractive angle. Okay, so now we want to calculate the largest distance, x, along the bottom face. So the limit for refraction, so that it's all totally internally refracted when it goes beyond this angle of incidence, is when the refractive index here, r, is equal to 90 degrees. That is the angle in air, because then that means that sine theta is equal to sine 90 is equal to 1. Okay. Okay, so what we've got is that 1.6 times by sine theta is equal to 1 on the other side, because it's 1 times 1. So sine theta, therefore, is equal to 1 over 1.6. You know you've gone the right way round because you've got an angle you've got a sine theta that's less than 1. So it's going to give us an angle that's less than 90 degrees. So we just do sine to the minus 1 of 1 over 1.6 to give us theta equals 39 degrees. Okay. Now, if we've got the angle, then we can work out. Now, quick trick here, if the radius is 100 millimeters there, it'll also be 100 millimeters here. It's difficult to see that sometimes, okay? So you've got the theta. In fact, we can go better than this. Sine theta equals x over 100 millimeters, if we just keep it in 100 millimeters. So actually, we didn't need to kind of like find the angle at all, because we've got sine theta, it's 1 over 1.6. So 1 over 1.6 times by 100 equals x. All right, and that comes out to be, should be, 62.5 millimeters. Okay, equals x. So sometimes it's just a way of seeing them. It's quite tricky, and you've got to be really quite, kind of like apply yourself and kind of like look at the, diagrams sometimes in a different way. Okay, so multimode glass fiber transmits light, and explain how it can't be transmitted successfully. Well, if you have a monomode fiber, let's just have a look at that, or kind of transmitted at very, very low angles to the axes, so that the signal that goes through down the center, then the distance will be, any signal going in, let's say a 0-1 signal going in, pulse going in, will come out, because as, a 0-1 pulse, i.e. you don't have any loss of signal with the transmission. You've got the distance is the same as the length of the fiber. Whereas if we have kind of like a mode which allows for different angles to just going down the center, you can see that between one angle and the center, that the distance traveled for some of the signals would be completely different and much longer for some signals compared to the other. So if you had a signal going in, all right, and two signals going in, then what's coming out is kind of like there's a little bit of a lost signal because it spreads out. And then you might get what we call this overlapping. And this overlapping kind of like interferes, and so you get this noise between the signals. So not only does the light take different paths because it's going at different angles, it's got different lengths, it takes different times so that the pulse is spread out. And the pulses then start to overlap if they are in a rapid sequence. So, and that spreading will, of course, increase if the distance traveled through the fiber optic increases. Okay, right, last one.
I think we are nearly up to 1/4 now, James. So I don't know if you want to go a little bit further. We're 14 minutes past at the moment.
Okay,
I don't know if you want
to... well, okay. Well, I think let's just look at this then in terms of it's another practical related experiment. I'll do a couple. I'll try and do it on a couple of minutes. So you've been given some plots. So what you've got to do is finish off and make a line of best fit. So remember, you'll need a sharp pencil, you'll need a ruler, and you will get a line. I won't be able to do a line. See, that's not a good line because I've got 3 one side, 1 on the other side. That needs rotating to give a better fit. But what you've got to do then is, once you've got drawn your line, you have to relate this expression y equals mx, say plus c, I'll put it in brackets there, y equals mx, to the equation that you've got, so that you've got v on the y-axis, you've got f on the x-axis. So that means that the gradient that you draw will be equal to h over e. And this comes in later because you have to work out a Planck's constant. So in the next question, you'll have to work out Planck's constant. So if you've got the gradient, you times it by e. Now remember, when you're doing the gradient, you have to do as big a triangle as possible and show the read-offs, show the triangle, and show the calculation. Now it says, and this is a common question, and this will come up in any of your units, discuss the extent to which the graph supports an equation of this form. Number one, it's a positive, it's a straight line. So it supports it because it obeys y equals mx. So m is equal to a positive gradient. So therefore supports it. Now we can see that it does not pass through the origin 0, 0. So c is a value. And in that equation, c should be equal to 0. Therefore, it doesn't obey that equation. So can you see they're trying to trick you a little bit, and you have to kind of like look at it from all different parts. So partly it does support and partly it doesn't support. But you could also mention that those points are very close to the line of best fit and therefore it does support and things like that. So you can add to it. Okay, and I think I've managed to squeeze that bit in without doing the reasoning, and I think I'll finish there. Sorry.
I think that's really helpful, and I think people will have a good stab at the rest of that question with that guidance and advice. So, I think it's certainly a goodbye from myself and Jane. It's a shame we didn't quite get through the whole paper, but I'm sure that there's plenty of helpful hints there to help you complete that on your own. So
okay.
It's thank you, Jane.
Okay, thank you very much, and we'll end now. Bye bye.